Hello everyone, my name is Luca Visinelli. I am currently a Fellini and Marie Curie Fellow at INFN Frascati National Laboratories. Starting this fall, I will be a Fellow at the Tsung-Dao Lee Institute in Shanghai and Associate Professor at Shanghai Yaotong University. At Cosmology from Home, I will discuss about methods to detect dark energy based on the two papers I have written here. We have observed the accelerated expansion of the universe since 1998 thanks to the measurements of the receding supernovae. We do not know much about the nature of dark energy. Is it a cosmological constant, a quintessence field, a modification of gravity, a phantom field, or what else? For example, a quintessential axion field of tiny mass would behave as dark energy. Please check these other papers of mine. There are still big uncertainties in the equation of state of dark energy. Planck alone favors a phantom dark energy model, while the inclusion of Baryon acoustic oscillations and supernovae reconciles data with the expectance from a cosmological constant of equation of state W equal to -1. Can we know more about the nature of dark energy from cosmology? This is what I have studied along with my collaborators Sanni Vagnozzi, Olga Mena and David Mota. In the paper, we have allowed for a non-zero scattering cross-section between dark energy and baryons, which can acquire relatively large values of order Barn. We find that data from the CMB temperature power spectrum and the matter power spectrum can accommodate for such large scattering cross-sections, up to the order of the Thomson cross-section sigma t. These results can be relied up to a comoving wavelength of order 0.1 per megaparsec, where nonlinear contributions become important and the analysis needs to be refined. Assuming that a scattering between fermions and dark energy exists, is there the possibility to study these effects in direct detection searches? The idea might sound crazy. However, the quanta of dark energy interact with baryons and electrons in various models. For example, both a conformal or a disformal coupling in the dark energy field of the energy momentum tensor of matter would lead to energy-dependent scattering cross-sections, whose cutoff scales, M1 and M2, are both constrained from LHC results. Can we reconcile these theoretical expectations with the results from XENONnT from last year? The XENONnT collaboration has reported an excess in the low energy recoil rate of electrons, with a significance of a few sigmas above the expected background. This result has received energetic attention with various proposals for its explanation, including the effect of axions produced in the Sun and of KV dark matter. For example, the axion, a light pseudoscalar boson which interacts feebly with electrons and photons, can be produced in the Sun through various mechanisms, which are described in the Lagrangian here. One such mechanism is the Primakov effect, which is dependent on the axion-photon coupling, or the atomic de-excitation and recombination, the Bremsstrahlung, and the Compton, or collectively ABC, which all depend on the axion-electron coupling. However, the best fit region of the axion parameter space from the XENONnT result is in sharp tension at more than 10 sigmas with the constraints obtained from stellar astrophysics. If xenon really detected solar axions, we would have a major problem in understanding how stellar objects cool off. An alternative proposal which does not suffer from this problem and is appealing is that XENONnT has detected dark energy quanta of a chameleon-like field. This is what I have explored in the recent paper with Sanni Vagnozzi, Philip Brax, Anne-Christine Davis and Jeremy Sackstein. Chameleons are fields of density-dependent mass. Their total mass can be derived from a potential which contains both a self-interacting part and an effective potential that describes the chameleon interaction with matter. The effective potential is derived from a fundamental Lagrangian that contains both the conformal and the disformal cases. However, we have shown that the disformal case is irrelevant in the solar production, which mainly proceeds through Primakov effect. For this, the production of chameleons occurs mostly in the regions of dense magnetic field, which in the Sun corresponds to the tachocline, a thin layer in which the energy transportation in the Sun switches from convective to radiative dominated. We have also modeled the XENONnT detection using the Lagrangian from the chameleon interacting with matter and radiation. In this case, we find that the disformal coupling dominates the process, and the cross-section differs from the results from the axion, being proportional to the energy of the chameleon to the fourth. The rate of detection per unit energy is then the product of the production and detection coefficients discussed before, times the number of targets in the XENONnT detectors. We show the results for the solar chameleon model in blue, for the benchmark couplings and energy cutoff for a best fit, in particular for the electron and for the coupling with gamma, with the photons. This is compared with the results from the solar axion model in red, obtained from the XENONnT collaboration. However, as mentioned earlier, there is tension between the fit for the solar axion model with xenon data and the results from stellar cooling. Chameleons do not suffer from this bound because of their density-dependent mass. In the core of the stars, the mass of the chameleon is much higher than the characteristic temperature of astrophysical objects, and the chameleon production is suppressed, so we evade the stellar bounds. To sum up, the future is exciting since methods to probe the dark energy sector are coming up. I discussed some seminal work on how cosmological and direct detection can help probing this part of the dark sector. In particular, the chameleon model could already be in reach of the next generation of direct detection upgrades. So, if the Xenon XS will be confirmed soon by either the Xenon upgrade or by other experiments, the unique features of the model could be tested in other complementary searches, for example ADMX. Thanks for the attention.